All right, 6.4, proportional reasoning. We're going to take a look at one of the things I alluded to in some of the questions you guys asked, that there's another way to do this kind of problem, and it's with proportions. So just so you know, proportions definitely show up in 6th grade. They did in my house just this past week. It was very fun. We had so much fun. Not really. I mean, my kids certainly didn't think that it was as fun as I like to think it is. So proportions come from ratios. So ratio notation is written as A to B, either as a semicolon or as a colon between, in a fractional form, or in words. There's two types of ratios. There's a part to whole ratio and there's a part to part ratio. So this example explains or shows the difference. So if you have 15 students and 7 of them make an A on the test, then the part to whole ratio is 7 to 15. 7 made A's, 15 to the whole class. The part to part ratio is 7 to 8. So 7 made A's, 8 didn't. So there's two different types of ratios that we talk about, and we will come back to these two different types of ratios later on in a different chapter as well. So to start with, if we were looking at a class, the ratio of boys to girls, we're told, is 2 to 3. And what we'd like to be able to do is to use that information to reconstruct what is the ratio of the boys to all the students. So when I think about this in terms of language. So I have 2, and it says, we do it in order, right? It says boys to girls. So the 2 represents the boys compared to every 3 girls. So units are going to be your friend on deciphering how to piece everything back together. So what that we want is we want the 2 boys compared to the whole class. Well, for every 2 boys, there are 3 girls, and this would be all of the comparison for the class. So we have 2 to 5. And again, you can write it like that. That's fine. If you don't like that, or you're afraid you might forget what that's representing, you can write it as a colon between them, 2 to 5. Or for another option, you can write 2 to 5 like this. Okay? So this would be the ratio of boys to the whole class. Now that doesn't tell you there's 2 boys and 5 kids, right? It just tells you for every 2 boys there are 5 kids, just like for every 2 boys there are 3 girls. And we can go the other direction as well. So this one actually tells you that if 3/7 of the class are girls, then we want to find the ratio of boys to girls. So this is saying that there's 3 girls to 7, I could put total, but I'm going to write down boys and girls. Like that. And I can break the 7 apart, of course, right? Into 3, which is the girls, and the 4, which would be the boys. So if we're taking a look then at the ratio of boys to girls, the boys is the 4, and the girls is the 3. Or 4 over 3. Or 4 to 3. Of course, you don't have to do ratio with boys and girls. You can do ratio with students and teachers. You can do ratio between ages. You could do ratio between heights, eye color, hair color, whatever you'd like. So those are some things that we could look at ratios for. So now that we have this sort of a definition of ratio, proportions is actually a statement that 2 ratios are equal. So A over B is a ratio, C over D is a ratio. If I put them equal to each other, that's a proportion. And there's some really helpful theorems that follow from here. The first one, Theorem 620, is probably lovingly in your mind embedded as cross multiplication. That's what you think of it as. It says if A, B, C, and D are real numbers, B and D are not 0, and we have the proportion A over B equal to C over D, or that equation, that it is a proportion if and only if A times D is equal to B times C. Now 621 and 622 actually show you that once you have one proportion, you have other equivalent proportions. So again, we have that same A over B equals C over D. But what you see on 621 is that they take both fractions and they flip them upside down. Okay, we could do that, right? If you have the same ratio of boys to girls on the left and right and we flip them both upside down, we're going to have the ratio of girls to boys on both sides. And it should be equal. And you can also notice that if you were to cross multiply, you still have that same set of AD equals BC that you did on theorem 620. Okay? Now, not only can you flip them upside down like this, interestingly enough, you can interchange a diagonal, and it doesn't matter which diagonal. So the theorem writes it as this diagonal that I've marked in green, but it's equivalently true that I could alter this diagonal and switch those letters instead. It'd be the same thing. Now, it feels a little bit funny, but again, notice that if you cross multiply, you still get A times D equals B times C. And what I will help you to notice as we do the problems is why that makes sense in a very contextual sense. Because, I mean, I can do some little, hand waving, moving the letters all around and show you that I can move the letters and that works. That's fine. But it's far more useful to see why it's practical to think of it that way from a word problem perspective. So we're going to do some examples. So there's always a comparison of something going on. That's what ratios do. They compare. So my examples earlier were boys to girls. We do that a lot with classrooms, in comparison. So this example doesn't use those comparisons. But what we want to do is we want to read through and try to figure out what two quantities are being compared. Because it's always two when we set up a proportion. There's always two quantities being compared. So Jim found out after working for 9 months that he had 6 days of vacation time. If he accrues vacation time at the same rate, how many days would he earn in 2 years? So what things are being compared here? Okay, so one comparison is the days of vacation. I need to change to a different color. That green was fine for just pointing things out, but all right, so my days of vacation, I didn't mean to underline it, compared to my months that I work, right? I have to pick months or years. I picked months because they're reported in both ways. But what else is being compared? What's that? The years can be changed into months, so that's not the other comparison. That's the same comparison we already have. There's something else that's being compared. It's not quite as obvious. No. This is the other comparison. What's happening now versus what happens later. Where he already stands now compared to what he wants to see or expects to see in the future. So here's the way that you can do the proportions then. You can either set it up so that it's days and months as a fraction, and then now versus later as the two sides of the equation. That's one way to set it up. We'll set it up that way. And then I'll show you another option. So what does he have in terms of the days of vacation he has now? 6. And if you want to write the word days, you can. I've got mine kind of written out to the side, so I'm not going to clutter up my numbers by having them in there right now. What is his months that he's worked at this point? 9 months. Now let's go to the other side of the equation. I don't know the number of days of vacation later. That's what I'm being asked to find, right? So this is the unknown quantity. How many months will he have worked in this future later period of time? A total of 24. That's the 2 years part, and that's, Emma, why I didn't need the 2. It's because I'm just going to turn them into months. Okay? Now let me show you another option of how we could have thought about it. Instead of doing the days on top and the months on bottom, I could have done the days on the left, wow, and the months on the right. And then instead of doing now versus later on the left and right, I could have done now on top and later on bottom. So if I set it up like this, the number of days he has now is 6. The number of days he has later, I don't know. The number of months he's worked now is 9. The number of months he will have worked later is 24. This is actually what's going on with this theorem 622. It's saying there's more than one way to set up proportions that are equivalent. So it doesn't matter which one you use, because what's going to happen next is you're going to cross multiply. And when you do your cross multiplication, whoops, that is not what I meant to click on. Let's go with that one. You will end up with 9x equals, what's 6 times 24? What? 144, okay. And over here, notice, the same thing happens, right? 9x on one diagonal, 144 on the other. That's why it doesn't matter. So if I then divide by 9, what do we get? 16. 16 days. Please make sure that you are including units when units exist. Okay, if 16 has some sort of quantity that it's measuring, it should tell me what it's measuring. This time it's days. Okay? Any questions on that one? Emma?
How come when we were doing the now and later and days and months, how come we didn't add 9 to the 24 month? Is it because those 9 months are already accounted for?
Yes. It's not asking how much will he have 2 years later. It's how much will he have in 2 years of working.
Okay.
It could have asked that, but it didn't ask it quite like
If
that.
it were to say
2 years from now? Sure.
You would add the 9?
Mm-hmm.
Okay.
Yeah. Or at the very end, you could add the 16 to the original 6 that he'd already earned. That'd be another way to do it.
Okay.
Yeah. Okay. Gracie.
I just have a quick question. I was thinking of doing it like the same way before I started going over it, but in my head I was like, oh, I should be converting 9 months into days, or like I thought I had to make the units the same.
Yeah. So we need the units the same in the sense of the comparison, but not in the overall problem.
Okay.
So we're going to have at the very end the number of days, but we don't need to work with the other quantity that's being compared so that it's in days too.
Okay.
We did use months, and we could have done years. So if you had really wanted to do years, maybe it would have been convenient in a certain circumstance. We could have taken, instead of doing 24 months, we could have left it at the 2 years, but then we would have had to have our 9 months represented in years. And for this one, that's not very friendly because that's a fractional value, right? Do keep in mind as you're working in this section of material, this whole chapter, and when you get to the test, you shouldn't be using decimals. In theory, I haven't taught you anything about decimals yet. That's not even theory, it's reality. I haven't taught you anything. I know you know stuff about decimals, but we aren't there yet. We're only working in fractions for the moment, okay? And I know that feels a little bit funny because you may prefer decimals, but the reality is that kids learn fractions before they learn decimals in school. So like conceptually building upon the progress of learning in school, this makes sense for us to only be talking about fractions and not even discussing decimals yet. So with the exception of money, kids talk about money early on, but they don't talk about decimals in general. So, all right, let's take a look at a map question. Okay, again, we're always going to start the question by asking ourselves what things are being compared. On a city map, a rectangular park has a length of 4 inches. If the actual length and width of the park are 500 feet and 300 feet, respectively, how wide is the park on the map? What things are being compared? Somebody be bold, tell me something.
The size of the city map,
Compared to what?
the actual size of it.
Okay, so the map compared to real life, right? So that's definitely one comparison. I'm just going to do that as my fraction. It doesn't matter if you don't want to do it that way, you can do it the other way. But we have our map sizes compared to what's actual life. What else is being compared? That's the map versus real life. There's something else, though.
Length and width.
The length and the width. That's the other comparison that's being made. So since I've set this up as my fraction, that means my length and my width are going to be on other opposite sides of my equality. So length and width. So there's my fraction and its corresponding sort of descriptions. So in the top left corner, we want the length of the park on the map. What is the length on the map? 4 inches. And just so that you can kind of see that we're paying a little bit careful attention, I didn't need to do this last time because the description was actually part of my units, but I'm going to put my 4 inches on here just so you can see it. If I go to the bottom, what is the actual length of the park? It's 500 feet. And please don't think we're going to change inches and feet into one another. That's not going to happen, and I'll show you why, but it is 500 feet. How did you decide it was 500 and not 300? There's a couple of ways, by the way. Emma?
Because this is the actual length and width of the park,
Okay.
and then 500 and 300, so like that correspondence.
Yeah, so whenever it says the word respectively, that means that you've got to go in order. So if length came first in the description and width was the second one, length would be first and width would be the second one. It's also valuable to note in your mind that when we talk about length versus width, length is the longer one. So that's another kind of clue for you. All right, how about the top right-hand corner, the width on the map? X, that's what we don't know. And then the width in real life, 300 feet. So what we want to see when if we do use units like I have right here, we want to see the feet along the same location, right? Feet are both on bottom. If I had ended up with inches on the top on the left and feet on the top on the right, that would be a problem. And I would have something sort of upside down, okay? But I don't have that. I have the feet lining up on bottom, and it's the inches that I'm going to be finding from my map on the top right. Now, for the purposes of cross multiplying, I'm not going to mess with my units. I just need to make sure I put them back on in the end because it gets kind of messy to write the units in the middle. So we're going to cross multiply. We have 500x, and then I have 4 times 300, which is 1,200. And if I divide 1,200 by 500, what do I get? What is it? 12 fifths. Okay, so it is 12 fifths. That is the reduced improper fraction. It's not a very good reasonable answer to somebody how long is something. You would never say 12 fifths, right? So we would put this back into a mixed number. Make sense? What would this be as a mixed number? Right, 2 and 2 fifths. So 2 and 2 fifths, what? Inches. As my answer. Okay, improper fractions have a contextual sort of weirdness in this particular problem, so we turned it back into a mixed number. Okay, next one. Kira and Dora worked 3.5 and 4.5 hours respectively on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths. Does any of you have fairness? Do you guys know I'm talking about strengths finder stuff? Some of you know. I have fairness. It's in one of my top 5. Fairness as one of her strengths. She wants to make sure that they're paid according to the time that they spent. Some of you are like, well, yeah, obviously that's what she wants to do. And others of you are like, oh, why bother? Just split it equally. It's okay. I know you. How much should each one earn if we split it according to the time they worked? All right, so there's a couple of different ways that you could set this up. Let's talk first that are actually distinctly different than we've talked about in the previous problems. But let's first just talk about the things being compared. What's being compared here? Time spent and the amount that they get paid. So the time that they're spent, comparing the two girls, and the amount that they get paid comparing the two girls. So one of the comparisons is going to be the time. The other one is their, I'll just write pay, I'm trying to see that. And then we've got Kira, and we have Dora. Okay, so how much time did Kiara spend? That one's 3.5. I know that I said don't use the decimals. We're just going to be cross multiplying here in a minute, so I'm going to write it in decimal form. If you want to write it in fraction form, it's not a big deal. But how about pay? How much did Kiara get paid? We don't know, right? That's the answer. We don't know. Right now, that's an unknown quantity. How many hours did Dora work? 4.5. And how much did she get paid? We don't know, but here's what we do know. If we had an amount for Kiara, we should be able to figure out an amount for Dora. How would we do it? Yep, 176 minus x. It's just whatever remains, right? Once one girl takes her part of the portion of the pay, whatever, we should be able to figure out what the other ones gets, because we know that they in total get 176. So I'm going to work this problem out with you this way, and then I'm going to show you. This one is the one that's maybe the most awkward to work out, to do it in this order, but the other one is a little bit more awkward to set up. So on this one, if I cross multiply, I have 4.5x on one side. On the other side, I have to be a little bit careful, and this is what I was talking about. This 3.5 has to multiply by the 176, and the 3.5 has to multiply by the negative x, both pieces. So 3.5 times 176, I have it written down. Is it 616?
Yes.
Good. And then the 3.5 times the negative x is negative 3.5x. I'll add my 3.5x to the other side. So 4.5x and 3.5x is 8x equals 616. Divide by 8, and what's x? 77. So we need to make sure when we get to the end and we answer the question that was actually being asked. Like, we can't just stop right here. We didn't answer anything at this point. It is $77, but what is it actually telling us? Yeah, that's Kiara's pay, right? Because that's where the X was located. This X right here represented how much Kiara got paid. So Kiara made $77. So how much did Dora make? 99. Now, I purposely left some space here because I want to show you the other way that you could set this up that's a little bit different. So I can still do the time and the pay. But instead of comparing the two young ladies to one another, I can compare one of them, I just chose Kiara because she was listed first, to the total that they both get, or did. So the Kiara side stays the same. She still worked 3.5 hours. She still earns X amount of dollars. Okay, that's still a thing. But over here on the total amount of time that both girls worked together was 8 hours. And the total amount of money that both girls made together was 176. It's not quite as a natural a way to set it up. But I don't have to worry about distributing the 3.5 through to the other two pieces when I cross multiply. And of course, you'll notice very quickly that you end up at the same place with 8x equals 616, just like we did on the other one. So it is another option. Gracie?
If we had like a different option to do it, would we be counted off?
No, it's up to you. I will say this, if the problem asks you, like if as you're working in the section 6.4, you better be setting up proportions. So if you set up equations that are not proportions, you're not doing what the whole point is of this particular section.
Okay.
Yeah. All right. At Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 25? So what is being compared in this scenario? Students and teachers. Students are more, so let me put them on bottom. We'll put the teachers on top. And the other thing that's being compared feels a little bit funny to write down, but it's the general ratio compared to the actual numbers or people, something like that. Right? Like they tell you that the ratio of teachers to students is 1 to 30, but they also tell you that there's 1,200 students. Does that make sense? Now, I know that there's another ratio up here about the 1 to a 25. This is a two-step problem because what they're wanting to do is they're wanting to know how many additional teachers they need to hire. So what we need to find out is how many teachers they have now with the 1 to 30 ratio, and then how many teachers they should have later with that 1 to 25 ratio, and then we can find how much off we are. So I can find out how many teachers we have now by cross multiplying here. So I have 30x equals 1,200. And if I divide by 30, how many teachers do I have now? 40. There are 40 teachers now. But I'm going to do the same thing for what we would really like the ratio to be, namely 1 to 25. Same 1,200 students. I'm going to call the numerator not an x because I don't want to confuse it with the x I already used. This really is a different quantity I'm finding. It's the teachers I want to have. So I have 25y equals 1,200. And I divide by 25. What do I get? 48. So this is 48 teachers now, 40 teachers now, and then 48 teachers that we want. Teachers wanted, we'll say. So how many more teachers would I have to add to my school in order to get to that ratio? 8. I would need 8 additional teachers. All right, let me run through these last couple. I'm not going to write a whole lot so that I can move a little bit more quickly. You guys can fill in the details for the writing part on your own later. Mary is working with measurements and writes up the following proportion. 12 inches over 1 foot equals 5 feet over 60 inches. I made mention earlier on that this idea of sort of making sure that things line up appropriately is important. So what do you notice happens on this particular one? Yeah, the inches and the feet don't line up, right? So the problem, this asks how would you help her? She actually has the ratios correct individually on each side, right? 12 inches and 1 foot is a ratio. It's a conversion factor. It's correct. 5 feet is also equal to 60 inches. It's also correct. So the individual sides, when compared separately, are correct. But of course, they're upside down from each other, right? So one of them needs to be flipped upside down, not both, but one of them needs to be flipped so that the conversion will be correct, that the ratios will actually form a proportion. So if I flipped my 60 over 5 upside down, then 12 over 1 would really in fact equal 60 over 5, and it would work. The other one here, Amy's friend, I mentioned this or alluded to this earlier. The friend tells her that the ratio of boys to girls is 5 to 6, and her friend mistakenly assumes that that means she only has 11 students. So what else could she have if she had a ratio of 5 to 6? She could have, like what? Say that again?
I don't know. I just said 25 to 30.
Okay, so she could have 25 to 30. In fact, let me write it as a fraction because this is equal to 5 over 6, right? So she could actually have, this would be a total of 55 students. And Gracie, I assume you multiplied by 5 on the top and bottom to end up with your 25 over 30. Perhaps that seems like, well, she probably doesn't have 55 students. That seems kind of funny. Well, maybe not, but maybe she has 10 to 12 and she has 22 students. that might be very realistic for your classroom, right? It's still a 5 to 6 ratio. So in talking to the friend, I mean, it's possible she has 11 students. If she were working in a small classroom, small rural school maybe, or maybe she's dealing with something that's in a special ed or something like that, maybe she does have 11 students. But maybe that 5 to 6 ratio is a reduced ratio, right? And if it's a reduced ratio, like 10 to 12 is equal to 5 to 6, she would have, notice, how are these numbers 11, 22, and 55 all, how are they all related? They're multiples of 11. So whatever she has a multiple of 11 students. So maybe she has 11, maybe she has 22, maybe she has 33, maybe she's the gym teacher and she does have 55. I don't know. They seem to have a whole bunch in there at the same time when they're in the gym classes. But it is going to be a multiple of 11, but it doesn't necessarily have to be 11. All right, so here's the deal. Group work and homework is all assigned. Between now and Wednesday, you should work on the group work first on the paper, just like you would if you were doing it in class, homework to follow, and you should submit it all to turn it all in or bring your questions with you to class on Wednesday. So we'll start with questions on Wednesday, and then we'll move into talking about the exam and what to expect from that afterwards, okay? Have a great week, guys.